everyone. Welcome to Learning at 11th Hour. This video is going to be about the multiplexer or the MUX. So I'm going to use an example to demonstrate that. So basically the multiplexer is going to handle multiple inputs and it is going to route them into a single output based on the control signals. So let me consider the multiplexer to be a box, a black box right now, and it's going to have multiple inputs. Say in my case, I'm going to consider 4. Example, there are 4 inputs and it is going to route it all through one output. It is going to have some control lines in order to channelize the inputs through the output. Since there are 4 such inputs, at a particular instant, only one input is going to be able to transmit its information to the output. So let's take an example. Say there are 4 devices: device A, device B, the device C, and D. These devices are connected to a network hub, which in turn is connected to the network. Now, at an instant, only one device is going to be able to transmit its information to the network through the hub. So we're going to put the multiplexer to use. So let's say we connect each of these inputs to the devices, and we have two control lines, say S0 and S1, and the output is connected to the network hub. So this is how it's going to work. When S0, S1 is 0, 0, then the output is going to be the message transmitted by device A. When it is 0, 1, it would be the message from device B. When it's 1, 0, it will be the message from device C, and 1, 1, it would be device D. Which means what? These control lines are going to be able to choose which input is right now going to be allowed into the output. So that is the job of a multiplexer. Having said this, we now kind of have a truth table over here, a raw one, which can be modified to find out what exactly is present in this black box. So let's see how we can do that. So say the input from device A is I0, from B it is input I1, I2 from C, and I3 from D. Now what we're going to do is we are going to replace these ABCDs with the output I0, I1, I2, and I3. So here we can actually form the expression that the output of the multiplexer, say F of the multiplexer F MUX, can be given as when S0, S1 are 0, 0, the output is I0, or when S0, S1 is 0, 1, the output is I1, when it is, or when it is 1, 0, it is I2, or when it is 1, 1, it is I3. So in either one of these cases, we are going to have an output from the multiplexer. So we can say S1 dash, S0 dash, I0 ANDed. This is the first term. Either this would hold good, or S1 dash, S0, I1. This is the second term. This might hold good, or S1 S0 dash I2, or S1 S0 I3. So this is the expression for the multiplexer. How did I write this out? So when there is a 0, I'll put a complement for the S1 and S0, and I'm going to AND it with that particular output. So if either one of these holds good, then the multiplexer's output value will be true, which means that if I0 is going to be, for example, right, suppose I have chosen S0 and S1 to be 0, 0. So that means what? S1 dash is going to be 1, S naught dash is also going to be 1. And this is ANDed with I naught. In all the other cases, these terms will become zeros, right? So this is going to be 0, this expression will become 0, this expression will become 0. So no matter what I1, I2 and I3 are, the combination of S1 and S naught in these expressions will make it 0. So when S1 and S naught are 0, 0, only this term is valid and I naught is ANDed with it, which means if I naught is going to be 1, then F MUX is also going to be 1. If I naught is going to be 0, F MUX is also going to be equal to 0. That is, when S naught and S1 is 0, 0, the output F MUX is nothing but I naught, be it 1 or 0. So this is the interpretation of this particular expression. Let us now try to implement the multiplexer using logical gates. So we have four inputs, uh, I naught, I1, I2, and I3. So I naught, I1, I2, and I3 are the four inputs. We have two select lines. So say this is S naught. Its inverted version is also used. So I'll put a not gate, S naught dash. We have S1 and S1 dash. So in order to implement this, what we can do is the first term S1 dash, S naught dash and I naught are all ANDed together. So I can take S naught dash and S1 dash and I naught and connect a 3 input AND gate over here. So this is the first term. Similarly, S1 dash S naught is ANDed with I1. So S1 dash and S naught connected to a 3 input AND gate. Then we have S1 S naught dash, S1 and S naught dash ANDed with I2, and lastly we have S1 S naught. So this is S naught and this is S1. We put another AND gate. So all of these AND terms are put together with OR gates. So if I consider that this is a 4 input OR gate, all these terms are going to be ORed together to form the final output, which is F MUX. So this is what is going to be available inside the black box. So instead of this, you can even replace it with three OR gates. So you can take these two to be connected to one OR gate, and these two to be connected to the second OR gate, and these two to be connected to the third OR gate. So instead of that, I've just considered it to be a 4 input OR gate. So this is the implementation of the multiplexer using logical gates. So there is a very specific relationship between the number of select lines and the number of inputs. For example, the case that we have considered, there are four inputs. So we will require 2 to the power x equal to 4. That means we require x select lines. So in this case, x turns out to be 2. So therefore, x here is 2, which means we need two select lines, S0 and S1, to select four inputs. Suppose I had just two inputs. Then 2 power x should be 2. So in this case, x will be equal to 1. So only one select line S would be enough. And in that case, my multiplexer would be 2 cross 1 MUX. That means two inputs, one output, and one select line. So that is I0, I1, and I'll call this as F as the output. So this is my 2 cross 1 multiplexer. Similarly, if I had 8 inputs, then 2 power x would be 8. So here x would be 3. So I would require three select lines, S0, S1, and S2. And the black box would be 8 cross 1 MUX. So 8 inputs starting from I0 up to I7 and just one output which is F, but three select lines S0, S1 and S2. So this way we can actually go on and find out how many select lines would be required for a particular multiplexer. So it should always be remembered that there are going to be multiple inputs and just a single output. Let us look at some numericals related to multiplexers which were asked in uh, the GATE examinations. So this particular question was asked in the EC paper in 2022. So the question goes like this. So there is a multiplexer which is a 4 cross 1 mux, and they say that there are four inputs A0, A1, A2 and A3. So obviously there are going to be two select lines and they have marked it as CD, and there is going to be one output, and the question says that this output is C XOR D. Then what should the values of A0, A1, A2 and A3 be, so that you get the output of the multiplexer as C XOR D? So here the first thing that we can do is we can write out what is the output of this multiplexer. So we know that this is say S1, this is S0. So 0 0 0 1 1 0 1 1. These are the possible combinations, and therefore we can say C dash D dash, when 0 0 is the select line's value, A naught is going to be selected. So A naught plus C dash D, then the A1 input is going to be selected. Next, C D dash, A2 will be selected, and then C D, A3 will be selected. Now it is really interesting to note the output of an XOR gate, right? So we know the XOR truth table. So for 0 0, the output is 0, 0 1 is 1, 1 0 is 1, 1 1 is going to be 0. So this is actually the truth table of the XOR gate. So this is pretty much what F should be, which means even A0, A1, A2, A3 should be these values. So that is an intuitive approach to this problem. So the values of A0, A1, A2, A3 would be 0, 1, 1, 0 intuitively. So let's check it out and see whether it is actually correct when we put these values in this expression. So basically we should get C XOR D, which is nothing but C dashed D plus C D dashed. So let's substitute these values here. So A0 is 0, so that means this expression is gone. A1 is 1, so C dash D is going to come here. A2 is also 1, so C D dash is going to remain. And A3 is also 0, so this expression is also gone. So we see that by substituting these values to A0, A1, A2, A3, which is nothing but the output of the XOR gate, right, which we found out intuitively, we do get the expression for C XOR D. So the answer to this question is A0 is going to be 0, A1 will be 1, A2 will be 1, and A3 is going to be 0. So this was asked in GATE in the year 22 in the EC paper. So let's look at another numerical where, which it's pretty similar, you apply the same principle. So here they have given us this multiplexer, which is a 4 cross 1 mux, whose select lines are P and Q, and the inputs are R, R dash, R dash, and R. So these are the four inputs, and there's going to be one output. So we have to find out the value of F for this particular combination. So they've given us four options, and we have to choose the correct one. So for this 4 cross 1 mux, let's find out the expression for F first and simplify it, and then we can match that with the options that are available. So here, what is f in this case? If this is what is given, right? So straight away we can write out the expression for it. So this is just for reference, right? So we have p dash q dash, which would select r. Then we have p dash q to select r dash. Then we can have pq dash, which would select r dash again, and pq will select r. So that is I naught, I1, I2, and I3 in this case, right? So let's simplify this expression and see what we get. So here, if we take r common in these two, what remains is p dash q dash plus pq. And if we take r dash common in these two expressions, these two terms, we get p dash q plus pq dash. So we know that this p dash q plus pq dash is nothing but p XOR of q, and we have r dash over here. And we also know that p dash q dash plus pq is p x nor of q. What is x nor? X nor is nothing but XOR bar. So we can say r into p XOR q the whole bar plus r dash p XOR of q. So if I consider p XOR q to be, say, some w, for example, then I can write this expression as r w dash plus r dash w. So this is again an XOR expression. So it is XOR between r and w, right? Now let me rewrite the w here. So that is r XOR p XOR of q. So the solution to this problem is f is actually p XOR q XOR and r. So there are other options where, so this was one of the options. The other options were p XOR q XOR r the whole bar. You know how we get confused with very similar close answers. But if you go through the entire approach in this manner, this is the solution we arrive at. So this is another problem. This is with a 2 cross 1 mux, and this kind of representation simply means that when the cell, for example, if I take this mux, right, say mux 1, so when x1 is equal to 1, the output is going to be output of this mux. If I say f1, okay, f1 is going to be a. That is what this 1 signifies. And when x1 is equal to 0, f1 is going to be b. So that is the hint that I'm going to give you. And I would like to encourage you to kindly try this particular practice problem, which was again a great gate problem asked in one of the previous years. If you have any queries regarding multiplexers, please do feel free to post them in the comments below. Thanks a lot for watching this video. I hope it was useful to you.